Math 30s. This video is going to be on lesson 7, which is called Pascal's triangle. The lesson is on page 415. What's going to happen is we don't have enough room to write this first example. So if you have a spare sheet of paper, I want you to take that out. Okay, what Pascal's triangle is on, it's going to be on the expansion of this binomial. So this is a binomial, x plus y, and we're going to be expanding this binomial and looking for patterns once we do the expansion of the binomial. So what do I mean by expanding that binomial? Well, what we could do is we could say first, okay, let's do x plus y to the power of 0. You know that anything to the power of 0 is going to be 1. And then what if I said, what is x plus y to the power of 1? Well, x plus y to the power of 1, simply x plus y. What if I said now x plus y to the power of 2? What would that give you? So you know x plus y to the power of 2 is x plus y times x plus y. It's that binomial twice. Once you do the distributive property, x plus y to the power of 2 would give you x squared plus 2xy plus y squared. I'm going to give you the expansion of x plus y to the power of 3, and then we're going to look at it and see if we could get patterns to figure out bigger binomial expansions. So x plus y to the power of 3 is the following. It would be x cubed plus 3x squared y plus 3xy squared plus y cubed. So what we're going to do is we're going to see what patterns that we could find, and then based on those patterns, you will actually be able to do the expansion of x plus y to the power of 4 really quickly, whereas if you were to do it by hand, it would take 10 minutes to do that question. Okay, so the first pattern I want you to see is the exponents. When this is raised to the power of 0, how many terms do you have? You've got 1 term. When it's to the power of 1, you have 2 terms. When this is to the power of 2, you have 3 terms. When this is to the power of 4, you have 1, 2, 3, 4 terms. So the first pattern that you should see has to do with the number of terms. If I say, what is the number of terms in the expansion, the number of terms, it was always 1 more than that n value. So the number of terms is going to be n plus 1. So if we're following this pattern, when we do the expansion of x plus y to the power of 4, there should be 5 terms. But why it's good to know that is the following. I could say x plus y to the power of 20. And I could say how many terms would that expansion have? It would have 21 terms. Okay, so that's one pattern that we could look at. Let's look at another pattern. This is to the power of 1, and this x is to the power of 1. Here's to the power of 2, x is to the power of 2. The power of 3, it starts with x is to the power of 3. So based on that pattern, this binomial to the power of 4, it's going to start with x to the power of 4. Now, there's other patterns that are going to happen with the exponents. So watch this. We have x to the 3, x to the 2. This guy would be an x to the 1, and there's an invisible x to the 0 here. X to the 2, x to the 1, there's an invisible x to the 0. So for my expansion of x plus y to the 4, first term's going to have x to the 4, then we're going to have an x to the 3, x to the 2, x to the 1, x to the 0. Watch what happens to the y's. There is no y here, so that'd be y to the 0. Here's y to the 1, y to the 2, y to the 3. So x's are descending and y's are ascending. So based on that, let's do our 5 terms. Let's set up our 5 terms based on what we know from the pattern. So first term is going to be x to the 4. Then second term is going to be x to the 3, x to the 2, x to the 1, and we're going to have an x to the 0. X to the 0 is just going to become 1. Then for our y's, this guy has a y to the 0, y to the 1, y to the 2, y to the 3, and this guy's going to have a y to the 4. Let's get rid of what we can. So I don't need this y to the 0. I don't need that x to the 0 because that just becomes 1. And then I don't need these powers of 1. Okay, so these are going to be our variables in each term for x plus y to the power of 4. And look, we've got 1, 2, 3, 4, 5 terms. Another pattern that I want you to see is I want you to sum the exponents in each term. So here's what I mean by that. If we were to look at this term here, we've got an x to the 2, y to the 1. 2 plus 1 is 3. Here we've got a 3. 2 plus 1 is 3 and a 3. Each term, the exponents sum to whatever that n value was. Same here, we've got a 2, 1 plus 1 is 2, and a 2. The exponents in each term sum to the n value. Let's double check that we're going to have a 4 for each of our terms. There's a 4, 3 plus 1 is 4, 2 and 2 is 4, 1 and 3 is 4, and 4. The last thing we have to do is we have to figure out what numbers go in front of each term. So that's going to be the coefficients. And what we're going to do is we're going to write the coefficients down here, and you'll be able to see that pattern. So what I mean by coefficients is I'm going to start with a 1, and then we've got a 1 and a 1. So let's write that down. So you've got a 1 and a 1. What else do we have? Over here, we've got 1, 2, 1. Then in this one, we've got 1, 3, 3, 1. And now we have to figure out what we're trying to figure out is what pattern is going to give us the coefficients for x plus y to the power of 4. So first thing you should see is the first coefficient and the last coefficient is all 1s. Then you say, okay, how did you get this 2? How they got that 2 was simply 1 plus 1 is 2. How did they get that 3? 1 plus 2 is 3. 2 plus 1 is 3. So if I said, what are the coefficients going to be in x plus y to the power of 4? Well, we know it's going to start with a 1, and we know it's going to end with a 1. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Those are going to be the coefficients of x plus y to the power of 4. So let's put them in. We've got 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. These are all going to be added together. And that is the expansion of x plus y to the power of 4. What I want you to do is see how quickly you could do x plus y to the power of 5. So we know, first of all, that n is equal to 5. This is our n. So we are going to have 6 terms. Okay. And let's figure out first the coefficients on each term. So bring down your 1s, and then you're going to add. 1 and 4 is 5. 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. There's going to be our coefficients. So 1, 2, 3, 4, 5, that's going to be 6 terms. What I'm going to do is I'm going to just give myself more room to spread those out. So I'm going to have a 1, a 5, a 10, a 10, a 5, and a 1. And then I'm going to do the patterns. If this is power of 5, x to the 5, x to the 4, x to the 3, x to the 2, x to the 1. I'm not going to bother putting x to the 0 over here. I'm not going to bother putting y to the 0, but I'm going to put y to the 1, y to the 2, y to the 3, y to the 4, and y to the 5. There is the expansion of x plus y to the power of 5. And we did that using these numbers here, which is called, this is going to be Pascal's triangle, and then we used our pattern. So that's how quickly you're able to do that. Okay, now you can move back to the book, and we'll answer, we'll fill in the book. So we've already done this, right? So x plus y to the power of 0 was our 1, and this is x plus y. And then here it was wanting us to expand to the power of 2, 3, and 4, but there was just not a lot of room here. Okay, state the number of terms in the expansion of. So remember that when we have x plus y to the power of n, the number of terms is always going to be that plus 1. So in this one, it would have 3 terms. The expansion of this would have 4 terms. The expansion of this would have 5 terms. And the expansion of this would have 21 terms. State the sum of the exponents in each term. So remember the sum of the exponents in each term. Okay, if we had power of 5 here, 4 plus 1 is 5. 3 plus 2 is 5. The sum of the exponents in each term is equal to whatever your n value was. So the sum of the exponents would be 2, 3, 4, and 20. Let's fill out Pascal's triangle. So 1's go along the edges. And then you're going to fill in by adding. How they got that 2 was 1 plus 1 is 2. So this would give you 3 and 3. This would give 4, 6, 4. And then you could do, it says explore a pattern in the triangular array and complete the next row in the triangle. So this one was 1, 2, 3, 4, 5 terms. That was x plus y to the power of 4, because remember that the terms is 1 more than the n value. So the next one would be x plus y to the power of 5, and the coefficients you'd have 6 terms. Your n terms are your 1, and then you simply just add to get the remaining terms. 4 and 1 is 5. 6 and 4 is 10, 6 and 4 is 10, 4 and 1 is 5. Okay, go to the next page, and we're going to now generalize the expansion of x plus y to the power of n. So in the expansion of x plus y to the power of n, if I said how many terms are there, it's that number plus 1. The sum of the exponents of x and y in each term is n. The exponents of x, remember it was x to the 5, x to the 4, x to the 3. The exponents of x decrease, and the exponents of y increase. And what happens with Pascal's triangle? It actually forms a symmetrical arrangement. Okay, so I'll show you quickly what this symmetrical arrangement would look like. So this arrangement here, how it's symmetrical is as follows. If I drew a line down here, the ends are 1s, and then once I go in, I've got a 5 here and a 5 here, a 10 here and a 10 here. So what you're going to see as we go further and further down, if you figure out what the first term is, that's going to be the last term. If you figure out the second term, it's going to be the second last term, and so on and so forth. Okay, this says use the patterns to complete the next 3 rows of Pascal's triangle. So I will let you do that. You might want to pause to do that. And the only thing that I'll write, if this is row 1, 2, 3, 4, 5, this would be row 6. So you are doing, that guy would be x plus y to the power of 5. Right? X plus y to the power of 5 would have 6 terms. So they want you to write the coefficients for x plus y to the power of 6, 7, and 8. Once you have that, You could then do the expansion of x plus y to the power of 6 and x plus y to the power of 7. So I won't do that for you because now you should be able to, okay, maybe I'll do x plus y to the power of 6 really quickly just to make sure. That's got to have 7 terms. The outer terms are 1. This will give me a 6, and because it's symmetrical, that's going to be a 6. This gives me 15, and that is going to be 15, and then we've got a 20. So x plus y to the power of 6 must have 7 terms. 1, 2, 3, 4, 5, 6, 7. It's going to start with an x to the 6 plus, we're going to have a 6. We're going to have a 15. We're going to have a 20. These are our coefficients. We're going to have a 15, a 6, and a 1. Descend your x's, x to the 6, x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, x to the 0, which I'm not going to put. Ascend your y's. There's y to the 0 here, y to the 1, y to the 2, y to the 3, y to the 4, y to the 5, and y to the 6. Make sure each term, the exponents sum to the n value. So n is 6, and the exponents sum to 6. Okay, this one. Which row of Pascal's triangle is equivalent to the coefficients of the terms in the expansion of? Okay, so what I want you to remember for this, or what we're going to jot down for this is as follows. If we have x plus y to the power of 0, that's actually going to be row 1, right? And then our second row was x plus y to the power of 1. That would be row 2. X plus y to the power of 2, sorry, would be row 3. So what you need to notice is when I ask for the row number, so this is just saying which row number would x plus y to the power of 6 be, the row number is always going to be 1 more than the n value. And the reason is because we have to start at 0, which is row 1. So this would be in row 7, that expansion, and it would have 7 terms. This would be in row 8, and it would have 8 terms. This would be in row 13, and it would have 13 terms. This would be in row, and then you'd say it was always that plus 1. And number of terms, n plus 1. Okay, flip your page. What you're going to see is you're going to see that Pascal's triangle, so these coefficients, can actually be written as combinations. So first of all, you have to know, like, are these questions, when we expand binomials, permutations or combinations? So it is going to be a combination, and I'll show you why. If I said x plus y to the power of 2, we know that that would be x squared plus 2xy plus y squared. That is the expansion of x plus y to the power of 2. Doesn't matter how I write those answers. So could I change it to be x squared plus y squared plus 2xy? Yes, right? That's the same answer. So because order does not matter, it is therefore going to be a combination. Okay, so let's see how we could write these coefficients as combinations, because again, there's going to be a pattern that you need to be able to see. So this first row, we know that that was x plus y to the power of 0. Okay. This second row, we know is x plus y to the power of 1. What I want you to notice is if whatever n is here becomes n there. So if n is 0, it's going to be 0, choose 0. If you type in 0, choose 0, you're going to get 1 as an answer. If this is 1, sorry, just to continue with that. So if this n is 0, you're going to have 0, choose 0. If n is 1, you're going to have 1, choose 0, 1, choose 1. So what I'm going to show you is let's say we had x plus y to the power of 5. That's going to be 5, and then here's the pattern. You always have to start at 0, right? Because we need to have this to be a 1. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, right? This row 7, we know would be x plus y to the power of 6. So n is 6, and we're going to have 7 terms, right? 1, 2, 3, 4, 5, 6, 7. But we take whatever n is, and we do n to the power of 0, n to the, or sorry, 6 choose 0, 1, 2, 3, 4, 5, 6. So again, patterns. What it says for this example is it says state the first 3 terms of the 8th row in Pascal's triangle. Okay, so the 8th row is x plus y to the power of 7. So that's going to be 7 choose 0, 7 choose 1, and 7 choose 2. Those are going to be the first 3 terms in the 8th row of Pascal's triangle. 7 choose 0, we know is going to be 1. 7 choose 1 on your calculator. So 7 math, go to your probability. 3 is 7, and 7 choose 2 is 21. So the first 3 coefficients in the 8th row are going to be 1, 7, and 21. Now remember, if I continue with this pattern, 7 choose 0, 1, 2, we would have 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, 7 choose 7. What the next question is asking is what is the last 3 terms in the 8th row? So the last 3 terms are these 3, but you know it's always going to be 7 choose 7, right? So it's always going to be that guy, and then it's going to be 1 less each time. 7 choose 6, 7 choose 5. Now, Pascal's triangle is symmetrical. If this is a 1, that's a 1. If this is a 7, that's a 7. If this is a 21, this is 21. We do not have to do this, and I will give you your homework. Sorry, I'll do the homework, and there's actually one homework question that I'm going to do with you, and it's going to be an exam question. Okay, so for your homework, I want you to do questions 1, 2, 3AB, 4, 5, and 6, 11, 13, and 15. Let's look at number 6, because like I said, this will be a test question. Okay, determine the value of n if the expansion of this has 14 terms. We know that the number of terms was that number plus 1. So if there's 14 terms, that number plus 1 is equal to 14. The number of terms, subtract 1 from both sides, or sorry, to get n, subtract 1 from both sides, and it's going to be 13. It would be the same for this. 26 terms, it's n plus 1, right? To get the number of terms, that's equal to 26. So if you simplify this, you're going to have 4n minus 2 is equal to 26, and then just solve for n. Add 2 to both sides and divide by 4. I just want to quickly check that the last homework questions are good. Yeah, the ones that I assigned, those are good questions. And then the next video will be on lesson 8. That's all for lesson 7.